All right. Good morning, everyone, and welcome to the IBM Qiskit Quantum Seminar series dedicated to you, the research and academic quantum communities. It's my pleasure to be your host here, Zlatko Minif from IBM Quantum Research. And as always, we'll be thrilled to roll out in just a minute this week's episode with Srinivasan Arunachalam from IBM Quantum. Now, I'm very excited about this one to learn about learning. So we'll have a lot of fun with that. Before we get started, we usually have a tradition to ask you where you're tuning in from. I see some of you are already on that. Today, maybe we can spice it up a little bit. And since I don't have a ready quantum joke for you, I'd love to hear what your favorite clean quantum joke is. So put that in the YouTube chat box, which is located somewhere on your screen, left, right, above or below. That's the same place where you can interact live with Srinivasan and myself during the presentation, ask questions, discuss, answer each other's comments. We usually keep it very lively and interactive here. That's also a great reason to click like and subscribe, because that's how you know when our next live seminar is coming up, Fridays at noon Eastern time. You can always go back and rewatch these, but the only time to really be live is Fridays at noon. And I already see, with a little bit of delay here between when we speak and when the comments stream in, we have folks from New York City, Colorado, India, Bogota, Dallas, and many other time zones. So thank you, folks, for making these, as always. So with that, it's time to get started. I'm your host, Zlatko Minif from IBM Quantum, and on this episode 163, I have the pleasure and delight to introduce you to my colleague, Srinivasan Arunachalam from IBM Quantum. Hello, Srinivasan. How are you today?
Yeah, I'm doing good.
All right. And do tell us where you're tuning in from.
I'm from California, San Jose.
All right. Well, you're also joined from people from Yokohama, Munich, Morocco, India, and a few other places still streaming in. Now, before we pull up your slides, Srinivasan, allow me to introduce you with a bit of a bio. So Srinivasan is a senior research scientist at IBM Almaden. Prior to this, he was a postdoctoral researcher at the Center for Theoretical Physics at MIT. In 2018, Srinivasan completed his Ph.D. from CWI and QuSoft in Amsterdam, Netherlands. And before that, Srinivasan finished his master's in mathematics from the University of Waterloo and the IQC. So with that, Srinivasan, the stage is yours.
Thanks, Zlatko. Thanks for the introduction, and thanks for the invitation to speak here. Like Zlatko said, I would like this to be as interactive as possible. So if you have any questions, like throughout the talk, you should just feel free to ping us and ask us questions throughout the way. Right. So this is I'm just going to give you like an overview talk today, like trying to explain what are some recent things I've been interested in, and where I've been kind of excited, what I'm being excited about. Right. So let's see. I mean, what's quantum computing? What's a quantum computer? It's just a computer that harnesses the power of quantum physics. And I think you might have all heard in the last 5 years, slowly we are rolling out with small quantum devices. Like IBM has its own device, Google has its own device, and so on and so forth. And the next natural question is, okay, what can a quantum computer do? Say in 15 years, somebody just magically gives us a fault-tolerant quantum device, and our engineering just gets there in 10 years. What can we do with such a device? And from a theoretical level, we do have a few answers. For example, from 94, Shor already came up with the algorithm for factoring. Given a number n, find p and q, the factors of p and q. We can do this in polynomial time classically, quantumly, and the best known classical algorithm scales super polynomial in the representation of capital N. And then the other de facto algorithm that we have used a lot in quantum computing is a search algorithm. So you have n items, n boxes, which are one of them is marked and the rest of them are unmarked. By marked, I mean one of them is 1 and the rest of them are 0. And the goal is to find the I for which the xi is 1. We know that you can get quadratic speed up. The classical algorithm takes time n. Quantumly, you can do it in time square root of n. And this kind of already quadratically improves a wide variety of algorithms that we might have seen in the past. So this is something else that's useful. Of course, the motivating idea for quantum computing by Feynman was the simulation of physics, all these works in Hamiltonian simulation are motivated by that. There have been several other places where you can get like quantum speedups, for example, like solving linear system of equations, gradient optimization, recommendation systems, graph algorithms, and then so on and so forth. And I think we have like approximately 500 quantum algorithms, and they've all just been compiled into this thing called Quantum Algorithm Zoo that you can find on Wikipedia. But as I mentioned, like we are still slowly building a quantum device, and building like having a fault-tolerant quantum device is a challenge. Like this is a hard engineering problem, and we're slowly making progress towards it. Like year by year, we're having more qubits, better fidelity, smaller error rates, and so on and so forth. But a natural motivating question is, sure, maybe it's a hard engineering problem, but are there any promising areas where I can look for a quantum advantage? Like, for example, of course, these algorithms are all like particular, like tailor-made algorithms. Like maybe for factoring, I can come up with an algorithm, searching another algorithm, and so on and so forth. But is there any other areas which kind of motivates where I can look for a quantum advantage? That naturally leads me to the motivation of this talk. It's about quantum machine learning. Like you have quantum, you have machine learning, both of them are hype. You just put them together. It's, of course, a great thing. And like you would expect, like quantum machine learning has received a lot of attention in the past decade. Like there's been a lot of works in this direction. But I think like one thing, like I think like if you go back to 2013, 2014, people thought you could get exponential quantum speedups for like many machine learning tasks. But then there was this dequantization and so on and so forth. It's been going back and forth. It's not super clear whether we have like a killer app in machine learning where quantum can give an exponential advantage. That is still a bit unclear to us. So I think as time progresses, we are realizing that it's not obvious or immediate that for a machine learning task, you can immediately get like exponential provable advantage for something that's interesting. But let me kind of quickly go over the works that people have looked at in QML. The first thing is like people have looked at classical problems and looked at quantum algorithms for those. Things like, for example, linear programming, semi-definite programming, gradient descent. Like gradient descent is a de facto algorithm for training neural networks, and we can get like quantum speedups for those. People have also looked at quantum problems and classical algorithms for those. Now, what do I mean by that? For example, you have this parameterized quantum circuit. That's what people are calling quantum neural networks. So you have this quantum circuit with many unknown angles in it. You can feed it classical data input, maybe get classical measurement statistics out, and then you run a gradient descent to find these unknown angles in this quantum circuit. So you can kind of view this as a quantum parameterized circuit, and you're kind of doing this optimization problem outside, which is with quantum statistics, and you're running a classical optimization on top of it. And then there are some works that I did a few years back is on quantum algorithms for learning theory. Like classically, if you look at machine learning, there are these two kinds of fields. Like one is just like practical machine learning, where they don't really emphasize too much on like theoretical level. They just would like it to work. So they just run it, and just like heuristically it does work. There's also this other side of classical machine learning called computational learning theory, where they would like provable speedups. So like in this model, if I want to learn this kind of functions, I can provably prove a speedup. So even in quantum, like one thing which I pursued is like, let's just go to this computational learning theory framework. In quantum, can we get like provable quantum speedups? So like if you would like to learn classical functions, given a concise description and things like that in a quantum way, can you get speedups? And we do know of certain examples where you could get some speedups of this sort. But one thing I would like to mention is like whenever you look at a quantum machine learning paper, there are always many assumptions, caveats, and things that go in. Like many papers claim polynomial speedups or even exponential speedups. You should always be careful. Like there are certain assumptions that went in to get these speedups. Now, in a way, like what I'm going to be talking for the rest of this talk is not really about themes 1, 2, and 3. It's something slightly more. It's quantum algorithms for quantum problems in some sense. So, for example, like learning quantum states has been a very active area from numerically and theoretically. For example, let's just say I have a noisy quantum computer. It provides me a quantum state out, a noisy quantum state. What was the state that this noisy quantum computer provided even? I don't know. And in order to answer this task, we need to even theoretically understand like what's really happening. If I give you copies of a noisy quantum state, how do I learn the state? So this is one area people have been looking at very actively, numerically and theoretically. As I said earlier, like there have been many works that have proposed like heuristics to learn these kind of noise and these quantum states and so on, promising fast algorithms, but these are fairly heuristic. And that kind of is like the motivating question for this talk. In a provable manner, can we learn quantum objects? Like I've been like being vague actually like purposely on what I mean by quantum objects. But the hope is like with provably, can I learn any sort of quantum object? When I mean provably, like like with this complexity, given these many copies of the state or these many accesses to my unknown quantum object, can I learn this object, which I couldn't have done classically? And for the rest of this talk, I'm going to be focusing on a few things. First, I'm going to be talking about learning Hamiltonians. Then I'm going to be talking about learning structured quantum states, stabilizer states, and phase states. Then I'm going to be talking about learning low-degree quantum channels. And then something called statistical learning theory, where, for example, if I don't have access to entangled measurements, I only have like measurement statistics, can I do something? Like, I mean, also, as you might have already guessed, like I've been trying to squeeze in like 4 different topics. So I'm not going to go to like proofs and things like that. I'm just going to give you like a high level idea of how these things work. What can we say? What is the current research directions in this area? And then maybe I'll just quickly conclude. And as always, if you have any questions about the things that I'm going to be talking about, please like post it on the chat there. Good. Let me start with the first thing. Let me start talking about Hamiltonians. Oh, actually, before that, let me just start talking about tomography. Like the most basic problem I think people have looked at for a while in quantum, and the complexity of it was resolved a few years back. So what's a quantum state? It's just an n-qubit quantum state. I just view it as a d by d matrix, where d is 2 to the n because it's encoding n qubits. It's trace 1 and positive semi-definite. And the question is, how many copies of an unknown quantum state are necessary and sufficient to learn this unknown quantum state? So again, rho is unknown, so it's a d by d matrix. If you're just more mathematically viewing this mathematically, how many copies of this quantum state are necessary and sufficient to learn this unknown quantum state, given copies of it? And more like from a pictorial perspective, like here's my quantum algorithm, QA. It obtains like rho tensor rho tensor rho, like many copies of rho. It can perform entangled measurements, separable measurements, whatever it likes. The goal is to output a sigma that is close to rho. It's a very basic task, and I'm not going to motivate it too much. Like, I mean, if you build a quantum computer, it's going to output a quantum state rho. Let's just say you can ensure that it outputs the same quantum state rho every time. And you would like to know what was this. For example, the goal was to produce a certain rho in your mind, but it produced rho prime. Can I test whether rho prime was equal to rho? So this is kind of, I view it as an experimental verification, or maybe even understanding the noise on how your goal to prepare rho became rho prime. So maybe that kind of encodes the noise in the system, which you could correct, and so on. So it's a very fundamental task. So as you would think, like there are d-square entries in this matrix, and estimating each one to error, say 1 over d square would take like d to the 4 many copies, and so. And so like a rough estimate would be d to the 4. That's like a very trivial algorithm, I would say. But information theoretically, there are only d-square entries in there. So you could maybe ask, could you do it better? And it was an open question for a long time. Like, what is the optimal complexity for tomography? That is, how many copies of rho do I need to learn rho? And only in 2015, I think it was completely resolved that the sample complexity of tomography is d square. And this kind of is optimal because kind of like there are d square entries in rho, and one can show like d square copies also suffice to learn rho. So this is known to be optimal. And of course, then the one thing that's kind of a little bit annoying is even for a 10 qubit quantum state, d is 2 to the 10. And so d square is 2 to the 20. So you need to prepare 2 to the 20 many copies of the quantum state to learn this unknown quantum state on just 10 qubits. So this just seems like exorbitant, like hoping to produce 2 to the 20 copies of the same state just to learn a single 10 qubit quantum state seems a little bit too expensive. And a natural motivating question is, maybe are there interesting subclass of quantum states? So recall, in this entire slide, I didn't assume anything about rho. I just said like rho is an arbitrary quantum state. But let's just say rho has some structure in it. Can I hope to maybe time efficiently learn it? And when I mean efficient, I mean polynomial in little n, not 2 to the n, and maybe sample efficiently learn it. When I mean by sample complexity, I mean the number of copies of rho. When I mean time complexity, how much time does the quantum algorithm take? For example, then you start looking at how many gates does it have to apply, whether these gates have come from a finite gate set, and so on and so forth.
I may be jumping ahead here. Can you clarify for us? So this d squared and d, is that using entangling measurements? I mean, I might be jumping ahead here in your talk. Is the framework here that each row is measured independently, or can you have joint measurements on multiple copies of rho? Maybe just clarify that for us.
Sure. So I wasn't planning to talk about it, but it's a good question. So the point is this d square upper bound is coming if I can perform a giant entangled measurement on d square copies. If I'm only restricted to single copy measurements, the right complexity is d cube. This is known to be tight, and we know the exact trade-off as well. Let's just say, for example, I'm only allowed to make measurements on like 10 copies instead of, say, single copy. We know the exact interpolation between making measurements on like t copies. When t is equal to 1, that is single copy measurements, the right answer is d cube. When I can perform a giant entangled measurement on all the copies, the right answer is d square.
And this is for some kind of additive error in some norm.
In the trace norm.
In the trace norm.
Yes. Even the epsilon dependence and everything has been pinned down. I just removed that for simplicity.
Yeah, that's okay. We'll come back to the other questions. Maybe we'll let you carry on here.
Sure.
Thank you.
Good. So the first thing, like I said, like the motivation for the first half of my talk is I'm going to try to understand, like, okay, just doing tomography, learning an unknown n-qubit quantum state requires complexity exponential in n. Maybe can I have some structure in my unknown quantum state and hope to learn it efficiently? The first thing I'm going to be looking at is called the Hamiltonian learning problem. So the question is like, H is a Hamiltonian, and I'm given Gibbs state of the Hamiltonian. Can I learn the unknown Hamiltonian? So this is my motivation. Let me tell you a little bit more on the setting more formally. So H is a k-local Hamiltonian. So it acts on n qubits for the time being, but all these components in this Hamiltonian act only on k out of the n qubits. So like you can view H as a summation of many terms, HIs, where each HI just acts on k out of the n qubits. And for every operator H, I can write it in terms of an orthonormal basis. Just think of the poly basis. And I can write it as a summation over I, mu I times EI. So think of EI as a favorite orthonormal basis of your choice. And it has a coefficient mu I. And the goal is somebody gives me copies of a Gibbs state. So what's the Gibbs state? Like, okay, I didn't mention what beta is here. So beta is the inverse temperature. Beta is the inverse temperature 1 over T. So for example, if I would like to prepare the Hamiltonian at an inverse temperature beta, the quantum state that would be present in my quantum system, like the equilibrium state, would be my Gibbs state. So if I give you copies of the Gibbs state, the goal is trying to find out what is the unknown Hamiltonian. The Gibbs state is a state you would have had if I had prepared this Hamiltonian H, and the only unknown thing in this Gibbs state is the coefficients mu 0. H is my unknown Hamiltonian, which in the poly basis looks like summation over I, mu I times EI. And EI is a known favorite orthonormal basis. Think of the poly basis for the time being. The only unknown here is mu i's. Somebody gives me copies of this Gibbs state rho at this inverse temperature beta, which is known to me. Can I learn these unknown mu i's? Can I produce like an epsilon approximation in the L2 norm? Right. So why did we look at this problem? So, I mean, there were a few reasons why we looked at this problem, because I think first, classically, people have looked at this problem of learning graphical models a lot. If I want to learn Ising models and things like that, they looked at it a lot. We just said, okay, fine. Learning Ising models has been well studied. What about quantum Ising models? And when you look at quantum Ising models, that's exactly this problem of learning Hamiltonians given copies of its Gibbs state. There have been several proposals to solve semi-definite programming using preparation of the Gibbs states. And so, but the point is, if you would like to experimentally implement them, the first question is, okay, let's just say this was my Hamiltonian in my mind, and I wanted to prepare this Gibbs state on a quantum computer. How can I be sure that I did prepare the Gibbs state that I had in my mind? So you can, again, view it as some form of experimental verification of actually preparing the Gibbs state of an unknown local Hamiltonian. So this was the kind of motivation that we looked at this problem for a few years back. And the main result that we had in 2020 was you can learn an unknown Hamiltonian given copies of its Gibbs state in complexity that's only polynomial in little n. So let's forget all the first three terms here. Let's only look at the last term here. So if you look at in the previous slide, I said, if you want to do tomography, that is learn an unknown quantum state rho, given copies of rho, the complexity scaled exponentially with little n. But now I looked at an interesting subclass of all quantum states. That is a class of Gibbs states of local Hamiltonians. And I've shown how to do tomography in complexity that's polynomial in little n, the number of qubits. It's no longer exponential in little n. So this was the main result that we had a few years back. Good. So for the next couple of slides, I'm going to give you a brief idea of how this algorithm works. It's going to be a little technical, but it's not going to be super technical. I'm just going to give you the high-level idea of how it works.
Quick question. Couple of quick questions. One from Jordan to clarify. What do you mean by local here? Is it geometrically local in the connectivity graph? Like which sense of local?
I will come back to that in a couple of slides. But for now, I'm assuming geometric locality. I'll come back to it again in a couple of slides.
Okay, great. Another question. So M here seems important, right? Because M could be polynomial, it could be exponential in N. What are the assumptions?
So if again, okay, good. So the point is I've been a little intentionally sloppy here. If I'm talking of local Hamiltonians, M scales polynomial in little n already. The point is if you didn't have any kind of like geometric locality, then M could be exponential in n. But if I enforce geometric locality, M scales polynomial in n.
Great. And I guess that holds for chemistry, typical chemistry Hamiltonian.
Sure. Yeah, yes.
Which is nice. Great. And okay, I guess what's interesting is that M doesn't go into, maybe give us some motivation for why M doesn't show up at all in the result.
So technically, if you assume like it's K local, M can be, and if it's a K local, K geometrically local, M scales polynomial in little n already. So kind of it's being hidden here a little bit. When I say polynomial of n cube, the point is M is already polynomial in n. So kind of like this polynomial of n cube kind of hides an M factor somewhere in there. So if I could have made M like explicit, but because I'm assuming geometric locality, M is already scaling as maybe n to the some constant.
Great. Okay, thanks.
Good. Right. So yeah, so let me tell you how we went about to solve this problem and kind of like how we eventually led us to the algorithm. So in the first line, I'm just going to recall the problem. I'm given copies of this Gibbs state e to the minus beta h, where h is my unknown local Hamiltonian, written in terms of this poly basis. And the goal is to learn these coefficients mu. That's the only unknown in this unknown quantum state rho. Everything else is known to me. So the first idea is you can do some form of shadow tomography. What is shadow tomography? Given copies of an unknown quantum state, I can learn the expectation value, all the poly expectation values well enough. And I can do this in sample complexity, this polynomial in little n. So that sounds a little bit good already. So the point is, given copies of rho mu, run shadow tomography, I learn the unknown, I learn all these expectation values well enough. Okay, that sounds interesting. The second observation we had is, okay, let's just say somebody gave us these expectation value EIs. How would I recover the coefficient mu i's? So we kind of write this entire thing as an optimization problem, which is now well known in quantum computing as this maximum entropy principle. The idea is just optimize over all possible quantum states. So sigma has to be just Ph.D, trace 1. It's an arbitrary quantum state. Just ensure that the trace of sigma times EI matches my unknown little EI. And just maximize the, now, subject a quantum state to these constraints, find the quantum state that maximizes the entropy among all the sigmas that satisfy these three constraints. This is a little bit of work, but one can show that the optimum of optimization problem 1, that is the quantum state that maximizes the entropy satisfying these three constraints, is exactly my unknown quantum Gibbs state rho mu. So if I could solve this optimization problem 1, I have actually learned my unknown quantum state rho mu. And if I learn this quantum state, I learn mu as well. So what I mean by learn, like for example, the output of 1 would have just been rho mu. So I just have it in a piece of paper. So I could have just gone down and just found out what's mu. Good. And okay, fine, this optimization problem is nice. And the one thing you generally do when you see optimization problems is just take the dual of it. And that's what we did. So this is my optimization problem 1 that I have here. I wrote the dual. And if I write the dual, that's exactly it's not again hard. Like if you just go down and sit on a piece of paper, write down on a piece of paper, the dual of this problem is exactly mu. Okay, this seems nice. So like the kind of use observation 1, find all these EIs. So I found this. I know this as well. I just find the minimization of lambda 1 to lambda m satisfying this thing. I just sit down and write it. And I found my mu, and that's the goal of the problem. Okay, so far so good. But there's a slight issue here. When you run shadow tomography, or if you learn any if you run any quantum algorithm, there's always some sort of an additive error happening. You can never exactly estimate any expectation value. So when I get EI, I might get EI primes, which are only epsilon away from the true EIs. So this is a slight issue, and we thought, okay, this should not be too hard. And like, for example, this was my original optimization problem. Instead of EI, I have these EI primes, because in step 1, I could only obtain approximation values, not the exact values. And if you look at the dual of it, again, the dual also has these kind of EIs and EI primes. And the main question to ask is like, how far is mu from mu prime? Like, for example, like a trivial bound shows that mu prime is actually very far away from mu. That's a trivial bound if you don't respect the fact that your Hamiltonian has some structure and so on. And the main question is, how far is mu from mu prime? If I solve this noiseless optimization problem compared to this noisy optimization problem, does noise really push you away from getting to the true value? That was the main thing that we had to answer. And that was the main thing that we did manage to answer. But the proof of this required was the most technical part of this work. What we did show is, if you look at this optimization problem is strongly convex, by which I mean, even if I perturb the parameters of this optimization problem, I do not go very far away from the true optimum. So instead of mu, which was a noiseless optimization problem, mu prime is a noisy optimization problem. If I do any perturbation, I still am close to one another. Yeah, that's all I'm going to be saying, and I'm going to be making a couple of comments. The first things first is our algorithm is sample efficient. That is, I just said the number of copies of rho necessary to learn rho is polynomial in little n, but it's time expensive. And you might have already guessed why, because you have to run this entire optimization problem. So you might be running in a landscape with 2 to the n many vertices, and so it's time expensive but sample efficient, which was the first when we wrote this paper a few years back. But the nice feature is kind of the only quantum part happening in our entire algorithm is step 1. If I give you an unknown quantum state, tell me expectation values of this quantum state. That's the only quantum part. Steps 2 is just purely classical optimization. And one more thing is, we have this annoying exponential dependence in beta and kappa, but this looks bad. But even classically, you have this exponential dependence on beta and kappa, and generically, you should not have been able to avoid if you assume some complexity theory, if you make some complexity theoretic assumptions. Yeah, but okay, I'm kind of highlighting my work, but the one thing I would like to say is there have been several works that happened after our works. The first thing is this work of Ha, Kothari, and Tang. What they showed is they actually improved our sample complexity from n-cubed to log n even. So they gave a dramatic improvement. But the point is, they need to assume beta is less than something called a critical temperature. But more recently, this work, but even their time complexity was exponential. Their sample complexity was exponentially better than ours. There have been this recent sequence of works by Bakshi, Tang, Liu, and Moitra, where they don't assume anything about the structure of the Hamiltonian. It need not be geometrically local. You need not write it, for example, in terms of the poly basis and learn the coefficients in terms of an arbitrary basis. I could have learned these coefficients. It was time efficient. They managed to learn the structure of this Hamiltonian. I think just in the last 1 year, they've had this sequence of 4 papers where they've kind of said, without making any assumption almost now, I think we are able to learn these unknown Hamiltonians given copies of the Gibbs states even time efficiently. I don't have time, neither do I have the knowledge to completely describe these works, but I would just like to say, okay, we started this area, looking at learning Hamiltonians given copies of the Gibbs states, and after a sequence of works, I think we now have time-efficient algorithms that do not make almost any assumption. That's all I'm going to be talking about learning Hamiltonians.
Great. A few quick questions then, maybe one from Jordan to clarify. The outcome of this is unique. So the state that you end up finding, in other words, is the optimal sigma is unique.
Well, technically, you're just running this optimization problem. You're getting a mu prime. I'm just promising you mu prime is epsilon close to the unknown mu. There could have been another mu prime that could have been. The point is, each time you run it, you might have gotten an E. For example, just if you look at E1, I would have gotten an E1 prime or an E1 double prime. Both of them are delta close to my unknown E1. But if I run these 2 optimization problems, my claim is mu prime would have been close to my unknown mu. Yeah. So I wouldn't say it's unique, but I would say it's close for sure. That's the goal.
Yeah, maybe I should have rephrased that. I guess it's unique for a given sampling set, for a given data
Sure.
set, but because the data set is random, you have noise, and so each time you get something different. And all of
That's
this, Mhm.
that is correct. Sorry.
And all of this assumes that the noise that you're thinking about is pure sampling noise, right? It's pure shot noise. It's not it's perfect measurements. You're just finite shot noise statistics. You're not assuming any bias in the measurement apparatus or any of this, right? That's separate.
In a way, kind of, I'm just saying, like, if you put in all the noise you would like in my running my protocol, I just eventually get an overall additive approximation of delta. This could be a cumulative nature of all the noise that had happened in the algorithm.
I mean, what happens if your measurement apparatus on some of the qubits is imperfect and you have a bit of a bias? So it doesn't just give you, if you should measure 0 on average, it doesn't give you 0, but it gives you 0.05, let's say, because there's some bias, not just statistical fluctuation.
Yeah, that's a question. I feel like that might come into the framework of already the noise that we're talking about, but I need to think a little bit more. I'm not sure.
Okay. Yeah, thanks. And maybe just motivate for us why maximizing, this was another question came up, why maximizing the entropies seems like of the state seems like the right thing to do. I mean, eventually you find out that it gives you the right answer, but before you know that.
Yeah. So the point is, the reason why this has been something that people in physics have looked at since the 30s, actually, since 1930s, is something called the Jane's principle, where Jane, like the person who wrote that paper, I think he already observed that the maximum entropy quantum state is the Gibbs state. If you ask me for intuition, I'm not super sure. Like, this is something known as a Jane's principle that's been used a lot in quantum computing, but actually in physics, like this dates back to almost a century back.
Okay,
It's a good question. I'm not very sure myself.
Thanks. And for the shuttle tomography, is this using? I guess here you're probably using. There's, from an implementation point of view, there's local shuttle tomography, there's global shuttle full Clifford tomography. I guess this is using the global, or does it matter?
I don't think it really matters. You can use your favorite shadow tomography protocol. Like earlier when I had the previous slides, we could have just used the Huang, Kyung, and Preskill's classical shadow protocol as well.
Like the original one, probably, because
Yeah.
I think the convergence for different kinds of observables is very different.
Yes.
Local versus global Clifford. So,
end of the day, we just care about k-local observables. So you could have used the protocol of the classical shadows.
Oh, you say that they're anyway k-local, so you probably don't need full global unitary. Okay.
Exactly.
Awesome. Great. Thanks.
Good. So let me move to my second part. It's about learning stabilizer states and more. So what's a stabilizer state? So we all know what's a Clifford circuit. It's just a circuit that consists of Hadamard gate, S gate, and the C0 gate. And the output of a Clifford circuit, when you run it on the all zero input, is just a stabilizer state. And these circuits are all classically simulable. So they don't give you universal quantum computation, but these are interesting classes of quantum states that one could just look at. There's an alternate way to write a stabilizer state. You can just view it as just look at the entire 4 to the n many Pauli matrices. Just pick a subgroup of them, call it little script s. That's a subgroup of the set of all Pauli matrices of size 2 to the n. And look at the quantum state psi that is stabilized by every Pauli matrix in script s. The psi that satisfies this is my unique stabilizer state. In other words, if you just look at the density matrix corresponding to psi, it is exactly just the quantum state that is the summation of all the sigma in the subgroup little script s. This seems a little bit technical, but the way you should think about it is like psi is like you just have this Clifford circuit in your mind. I run it on all zero input, and the quantum state that I get out is my stabilizer state. This is a structural characterization of all stabilizer states. There is this protocol that in the last couple of years has become very popular and a lot of people have been using. I would just like to tell you a little bit about it. It's something called Bell sampling. So what's the Bell basis? So For example, like everybody knows the 0, 0 plus 1, 1. That's an EPR state. You could also look at 0, 0 plus 1, 1, 0, 0 minus 0, 1, 1, 0, 1 minus 1, 0, and 0, 1 plus 1, 0. If you look at just these 4 states that I just said, this is called the Bell basis. And a slightly technical way to write what I just said is you can just look at, for B being in 0, 1 to the 2, that is just all 0, 0, 0, 1, 1, 0, 1, 1. WB are just 4 quantum states, which are called the Bell basis. And like I just said, like these form an orthonormal basis, and phi plus is just the EPR state. So there is this protocol called, okay, what's the learning task here? I give you copies of this unknown quantum state psi, learn psi. And right, and the question is like, okay, the circuit that produces psi was classically simulable, so most likely this state should be learnable. And we didn't really have an algorithm formally written down. Like it was kind of folklore by a work of Aronson and Gottesman in 2003 that you can learn these states in polynomial time, but we didn't have like a formal way written down. And in the last few years, people have been looking at this Bell sampling procedure, which I'm going to talk about next, and kind of extending it to learn even more complicated circuits than just Clifford circuits. So what does Bell sampling do? It just takes like 4 copies of this quantum state psi. Now, let's just start with just 2 copies. Let's forget the last 2 copies. Let's just take the first 2 copies. So the first copy is on n qubits, the second copy is on n qubits. What do? I just measure qubit 1 and n plus 1, 2 and n plus 2, 3 and n plus 3, all the way to n, 2n. I measure all these 2 qubit pairs, I, n plus I, in the Bell basis. So recall the Bell basis is nothing but a measurement acting just on 2 qubits. So I measure qubit I and n plus I in the Bell basis, and I get like n and n bit output, x. So I'm going to call it B1, B1 prime, Bn, Bn prime. So I'm going to call this string x. So I take 2 copies of the state, I measure in the Bell basis, I get the string out. And I repeat this with the second 2 copies, I get another string y out. And I'm just going to output x plus y, that's it. So surprisingly, the observation is if I measure an unknown quantum state psi in a Bell basis, I'm actually producing a stabilizer of my unknown quantum state. And as I said, we know the stabilizer states have this nice structural decomposition. So if I would like to learn a stabilizer, I would like to learn a basis of this script S, I just told you a way that takes 4 copies of this quantum state, produces me a basis of this subgroup script S. And we know the subgroup has size 2 to the n, so there are only n basis vectors. So each basis vector I learned with 4 copies, so I can just I just repeat this n times, that's it. Yeah, so let me just tell me what's happening here. So I just took like 4 copies of this quantum state. I did Bell sampling. So it takes a little bit of work, but not too much work, to see that the output of Bell sampling actually produces for me a basis for this unknown stabilizer group for my unknown quantum state psi. And because we know it's a subgroup of size 2 to the n, it has a basis of size little n. So I just need to take essentially n many Bell sampling. I need to repeat Bell sampling on 4n many copies, each time on 4 copies. I get n basis vectors out. And once I get n basis vectors out, the span of it is exactly my stabilizer subgroup, and I learned my unknown quantum state. So this is yet another class of quantum states, which I can learn actually in polynomial time. Recall, psi is an n-qubit quantum state. If I just did the naive tomography protocol, that would have taken me 2 to the n many samples. But now, I could have actually learned this. I just gave you a procedure to learn this quantum state with just n samples and time n cube. So this was something that Montanaro kind of formally wrote down in 2017. And since then, there have been several works that have kind of gone beyond stabilizer states. So like I mentioned, like stabilizer states are produced by Clifford circuits, which we know to be classically simulable. You could add a T-gate to make it universal, but how does the complexity of the algorithm change when we add more T-gates? So that's something there have been, like, as I mentioned, there have been like these works of Grewal, Iyer, Kretschmer, and Liang from UT Austin. They've had this sequence of papers, and then there have been few other papers in the similar line where they've showed how to learn states produced by Cliffords plus T-gates in time n, 2 to the k, where k is the T-gate complexity. I don't have too much time to go into the proofs of these, but the idea is kind of, I will just mention a very high-level idea that they are structural observation that they make. So let's just look at the set of all stabilizers for the states produced by Cliffords plus k many T-gates. And if you look at all the stabilizers, one thing that they observe is this set of stabilizers have something called stabilizer dimension, at least n minus k. And again, they use crucially Bell sampling. They're just saying, let's learn the stabilizer basis using using Bell sampling. Once I learn the stabilizer basis, I'm going to do some sort of like a small protocol on top of it. And yeah, essentially they're saying I can learn the unknown basis for my stabilizer dimension and using k samples. So I kind of do tomography on k qubits, which is a non-Clifford part that takes time 2 to the k, and just run my Clifford running protocol on just like n minus k qubits that takes time polynomial in n. So you have polynomial in n, comma 2 to the k. The 2 to the k is taking care of the non-Clifford part because there k many t gates. The polynomial in n minus polynomial in n is taking care of the Clifford part of the state. Again, I don't have too much time to go over it, but that's all I'm going to be saying.
And Srinivasan, maybe on the previous slide, a quick question on the intuition here for how and why 4 copies. So, this reminds us a bit of like teleportation, say, where let's say if I have 2 qubits, I put in a Bell state, there's a Pauli on one of the wires, and then I measure in the Bell basis. And in that case, what happens is that the Pauli check vector, which is your f2 to the 2n in that case, n is 1, let's say, gets mapped to the output bit string distribution. But that's only 2 copies. I mean, here you have a more complicated object because it's not a single Pauli, it's the superposition over all the Paulis in this calligraphic S group. Does the same intuition still hold? It's just the 4 copies somehow allow you to map all the Pauli check vectors to the output. Maybe give us some kind of intuition here.
Actually, it's very similar. So the point is, in teleportation, you have this unknown, like say 1 qubit or 2 qubit quantum state. You do this teleportation, and once you measure in the Bell basis, you can do this correction matrix based on the output that I got. In a way, if you view it, the procedure that we have just on the first 2 copies, that is kind of telling me like what is a state that stabilized my unknown quantum state. For example, if I knew it was just like b equal to 0, 0, that means I realized that I learned an unknown stabilizer for the state, which is just the identity. So I don't need to make any change. But if I got the outcome 0, 1, the change that I need to make in order for a stabilizer, for example, a Pauli to be a stabilizer of the state, is going to be the X matrix. So that's the change in teleportation. Does that help a little bit?
Just repeat the last part about.
Right. So if I just take 2 copies of this quantum state, and let's just say it's acting only on 2 qubits. So like I'm just going to measure qubit 1 and 2 because I is equal to 1 and n is equal to 1. I measure qubits 1 and 2. When I measure 1 and 2, I'm going to get, for example, let's just say I got the outcome 0, 1. When I got the outcome 0, 1, what do I know? So it kind of tells me that the X matrix kind of is going to be a stabilizer of my unknown 2 qubit quantum state. But this X matrix what is happening in teleportation? In teleportation, it's saying like once I got the outcome 0, 1, I need to perform an operation on the X times psi in order to recover my unknown quantum state psi. But the point is, if I just perform X on my unknown quantum states X times psi, I actually get back the original quantum state psi itself. So in a way, like this is telling you some form of a syndrome measurement that you would need to learn my unknown quantum state. That's essentially what's happening in Bell sampling.
Mm-hmm. Mm-hmm. Oh, okay, yeah, I see. You're saying you can kind of see it as a syndrome measurement as well.
Exactly.
Yeah, that's nice. Mm-hmm. Thank you.
Good. That's all I'm going to be talking about learning stabilizers. So this is yet another class of interesting quantum states which I can learn efficiently. So for the next 5 minutes, I'm going to be talking about another learning model that we introduced and just talk of some limitations of that. Like good and bad things about it. Actually, yeah, okay. We did have this work recently with some people where we looked at learning something called phase states. So if you look at, you could just view what's a phase state? It's just a state which is a uniform superposition over -1 to the f of x, where x is an n-bit string with a uniform superposition 1 over square root 2 to the n. And the question is, how many copies of psi f are necessary to learn f? This looks very abstract for the time being, but there are several motivations for this. The first is kind of like, you can view stabilizer states as, if I fix the degree of f to be 2, it encodes stabilizer states. And we know, like, for example, pseudo-random functions, that is f is pseudo-random, then the corresponding ensemble is actually a pseudo-random quantum state that is indistinguishable from hard-random quantum states. If you look at IQP circuits, that are circuits which are not simulable, they kind of correspond to the states psi f when the degree of f is 3. And there have been a few works in recent years that have looked at kind of just using phase states for building like crypto primitives and for other complexity theoretic results. So kind of motivated by all these reasons, we kind of saw these kind of states appearing in all these works and kind of thought, can we learn these kind of quantum states maybe efficiently, or what's the complexity of learning them? So in some work that we did with Ted Yoder, Sergey Bravi, and Arkopal, we kind of get like optimal bounds on learning these kind of quantum states. The complexity is not great. It's like kind of n to the d. But if d is small, like when d is say 3, like you can learn outputs of IQP circuits actually in polynomial sample complexity and even in polynomial time, which we found a bit surprising, that this class of states are actually not simulable, but the output states are actually learnable in polynomial time. Good. This kind of, now I'm going to be talking about this another learning model altogether. So this is the without entanglement part of the title of my talk. Good. So let's just say, so far, what did we do? We said the following, right? I give you copies of this unknown quantum state psi or rho, and the goal was to learn this unknown quantum state. So I'm going to, for the next couple of slides, I'm going to restrict myself to a simple class of quantum states. So the amplitudes are all just plus minus 1 over square root 2 to the n. So think of C as just a number, C of x as just a number minus 1 comma 1, and C is just a Boolean function that takes n bits and maps it to minus 1 comma 1. So what's an entangled measurement? Like this was something that Zlatko asked in the start of the talk. Like an entangled measurement just takes like t copies of my quantum state and makes a giant entangled measurement on it. So that's something called entangled measurement. Then there's something called single copy measurements or separable measurements, where I just take one copy of psi, make a measurement on it, take another copy of psi, make a measurement on it, so on and so forth. But we kind of introduced this model of statistical query model, where kind of maybe even entangled measurements and separable measurements are far away from near term. Maybe if I just want like near term right away, if I want to implement something, preparing the same t-fold tensor copy is clearly out of reach. But maybe even preparing a single copy, all my n qubits coherently, maybe it's hard. Maybe it's possible to get expectation values well enough. Like that was like one of the experimental demonstrations that we had last year, where you could get expectation values well enough. And a few years back, we introduced this model of quantum statistical query model. Like we thought this would be a natural model, where we said, like, let's just say you give me a 2 outcome measurement, m comma identity minus m. So a QStat oracle, it's a statistical oracle, takes a copy of psi, performs the 2 outcome measurement, and tells me an approximation of the 2 outcome measurement well enough. So it takes the 2 outcome measurement m, think of tau as just a constant for the time being. It's going to output a number alpha subscript m because it took input m, and alpha m is going to be close enough to the probability that the 2 outcome measurement applied on psi accepted or not. So it kind of gives me an expectation value of psi with respect to m. And the question is, how many copies of how many statistical queries are sufficient to learn my unknown quantum state? And the reason that we thought about this is kind of like, let's just say you had like only a couple of quantum computers out there, but many of the clients are kind of like sitting all around the world, but they don't have access to like implement this quantum circuit on an arbitrary input of their choice, quantum state of their choice, and so on. What could they do? They could just tell the cloud, okay, I have this quantum state in my mind. I hope you could prepare it. Let me give you this measurement m. Could you tell me the expectation value of this measurement m with respect to my unknown quantum state? So the learning algorithm is purely classical, but the interface is with the quantum computer. So you could kind of say, like, let's just say IBM has a quantum computer, but my client is purely classical. The interaction is purely classical, but my learning algorithm could be doing a quantum learning procedure when interfacing with a quantum computer. And so one thing that we looked at, like in a subsequent paper last year, is can all classes of quantum state maybe learned this way? Like, could I learn arbitrary quantum states in the statistical query model where I just have expectation values? So before this, like in the first paper where we introduced this model, we gave a lot of positive results, but we thought that kind of motivated us saying, okay, maybe like all quantum states could be learned in this statistical query model. But we said, like, even the simplest class of stabilizer states cannot be learned in a statistical model. So stabilizer states, which I just showed you, could be learned with just like n copies of this quantum state using Bell sampling and so on. It kind of required this intricate 2-copy measurements. Like I had to take 2 copies, measure in the Bell basis, take another copy, measurement in the Bell basis, and so on and so forth. But could I just make it single copy? With just single copies, could I have just maybe learned the stabilizer states? So that was something that we did last year. One thing that we showed is like the simple class of just like a subclass of stabilizer states cannot be learned with just expectation value measurements. And in fact, we showed like if I just give you expectation value measurements, my sample complexity goes up exponentially. It scales exponentially with n. But with the entangled measurements, I showed you a protocol that takes n copies. With separable measurements, we know that you can do it in n squared copies. Yeah, that's all I'm going to be saying here. I'm going to be quickly talking about one more thing before I wrap up, actually. Is that fine? Like, do I have like 5 minutes? I'm just going to assume it's a thumbs up.
Yeah, you're good.
Okay, thanks. But yeah, maybe the theme of this is like there is this learning model that we introduced where you just don't have, you can just obtain expectation values of an unknown quantum state with a mesh observable of your choice. What is the power of just obtaining expectation values? And this work kind of like looks at this model and theoretically shows that there is a simple class of quantum states, basically stabilizer states, for which just obtaining expectation value measurements is not good enough. You need to obtain something more than that to learn this class. Good. Yeah, the final thing I'm going to be talking about is learning quantum processes. So like I looked at learning Hamiltonians. That's my first part of the talk. Then I looked at learning structured quantum states, where I looked at learning stabilizer states, then Cliffords with some T gates, and then phase states, and then learning without entanglement. But what about learning quantum processes? So this is something called process tomography. So this is well known in quantum computing. People have looked at it a lot. So just think of a unitary U that maps CD to CD. It takes like n-qubit quantum states, so D is dimension. It maps d-dimensional vectors to d-dimensional vectors. And I'm given access to this unknown quantum unitary U. That is, I can feed it psi of my choice. I get out U applied to psi. And the question is, how many times do I need to interact with this unitary U in order to learn the unitary U, say up to Frobenius norm or something of that sort? And there, like tomography, we know like good bounds on this learning task, and the right answer is d square. Again, like d square again should be very similar to tomography. Even in tomography, when we had a d by d matrix, which is completely unknown, could we have learned this? Could we have learned this unknown quantum state? The sample complexity scaled with d square, but now even with unitaries, it's well known that the sample complexity of just unitary tomography is d square. One thing we looked at is something, for example, this unitary has some structure in it. And the structure that we looked at is called low degree. So again, like, for example, like, again, like the motivation for my Hamiltonian learning task, Hamiltonian learning problem and stabilizers is you look at some unknown quantum object, write it in terms of the Pauli basis. Let's just say the coefficients have some structure in it. For example, in the Hamiltonian learning problem, I just said like on the only Pauli terms that survive are just like K local Paulis. In stabilizers, we know that these Paulis have some subgroup structure in them. And for unitaries, I'm just going to assume that the Paulis are just low degree. And what I mean by low degree is, for example, all the high weight Paulis have 0 mass on them. So for example, all the XXXXX all the way to N, the coefficient of U on that kind of high weight Pauli has to be 0. Only on low weight Paulis can we have some weight on. So this is a class of unitaries that we looked at in recent work. And the question we asked is like, how many uses of such a unitary suffices to learn an approximation of the unitary? We also looked at low degree channels in our paper, but I won't be talking about that. And let me tell you a couple of motivation as to why we kind of looked at it. One thing is, for example, if you want to implement a quantum channel or a quantum unitary on a quantum computer, we know there is going to be noise in the quantum system. But noise kind of more often than not just kills the high degree terms, because like, for example, if I have a high degree term, noise is applied like n different times. So the point is when I apply eta, for example, that's a noise damping factor applied to the power n, that is going to be much smaller. So it's going to be very tiny on high degree terms. Only on low degree terms will the noise not make a difference. So in some sense, you could think of like running an unknown quantum process on an unknown quantum computer as inherently implementing a low degree quantum process, because the high degree terms are anyways going to be killed by the noise. So that was one of the motivation as to why we thought this would be an interesting learning task from provably. And one of the main results that we showed is actually I'm overusing D in the slide. I'm sorry about that. So the D in this here and D here are different. So if it's degree D, we show that the sample complexity scales exponentially in D, but it's independent of the number of qubits altogether. Sorry, I mentioned D and D here. Sorry. The point is this D is the degree here and this D is the dimension here. So the sample complexity of learning an unknown degree D unitary scales exponentially with D and is totally independent of the dimension on which the unitary acts on. So this is very surprising. It doesn't even depend on the number of qubits. As long as I'm promised to be low degree, that's all matters. I'm just going to give you a quick overview of the proof idea. Actually, I'm going to skip the proof idea. I don't think it's something that came out like a week back. This was with Arco Paul, Fran, and Carlos Paletuelos. So this paper just came out a month back, and I'm going to skip the proof sketch, and I'm just going to conclude. Good. Yeah, let me just conclude. Yeah, like I said in the start of this talk, like quantum machine learning, it kind of combines two exciting fields. Like, that's what you would generally do. Like quantum computing is like a very exciting field. Machine learning is very exciting. If you combine them, like it's a double the hype or double the excitement. That's one reason why a lot of people have been looking at this. There are several problems for which quantum can give like exponential speed ups, but like more often than not, I always tell people like you have to be very cautious as to what are the assumptions that go in there. What is my learning model? Maybe I have some sort of like extra access which I didn't have earlier in the classical model, and so on. But I still feel like as we have more and more noisy quantum devices, and we like, I think kind of understanding like learning the noise in the quantum system or learning noisy quantum states, I think we still don't know how much is possible and how much is not possible. And I think that's a very interesting line of research. It's definitely worth understanding like what is the strength and limitations of quantum machine learning when you have noisy quantum devices. I definitely think that's like a very promising direction to look at. With that, I thank you for your attention.
Thank you very much, Srinivasan, for the great talk and many results. Yeah, this might be one of the talks with the most results we've seen actually in 163. So congratulations. Few questions, folks. This is a great time to post your final questions here in the chat box. We also finished a few minutes early, so fantastic. Maybe just a very elementary clarification to begin with from Rudra. How do you get multiple copies if there's no cloning theorem in play? Maybe just describe a little bit the setup you have in mind here for us.
So no cloning says like if I give you an unknown quantum state rho, I cannot produce two copies of rho. But the point is, let's just say there is a server, like IBM is a quantum server. It, for example, said like because IBM knows rho altogether. So think of it two ways. Like you're the client, IBM is a server. IBM knows that this is my quantum state I want to produce. So it can run the same circuit twice and produce two copies of rho. It doesn't. In no cloning, you don't know the unknown quantum state, but here IBM as a server can produce two copies of the quantum state because it knows the circuit that prepared the quantum state. So it could have just run the circuit twice and prepared the quantum state. And from a learning perspective, you think that IBM has produced two copies of the quantum state, and you would like to learn what is the unknown state it produced.
From Kiran, are there relations between simulation and learning?
That's a good question. So like one of the motivations for this sequence of papers on extending learning stabilizer states to states when they have only k many t gates is they wanted to kind of mirror the same thing that you obtain in simulation. In simulation, we know how to simulate an arbitrary Clifford circuit with k many t gates in time polynomial in n, comma 2 to the k, where k is the number of t gates. And they observed that that's also the limits of learning states which are produced by these things. They kind of showed, I think, in their paper that if you are more than, you cannot hope for a better than poly of n, comma 2 to the k in terms of learning. And that also seems to be a limitation of simulation, assuming BQP is not equal to BPP.
Mm-hmm. That's a very interesting connection. You looked at learning local unitaries with local terms, but oftentimes the terms might not be local in like the exact poly, but they might be local in a different sense, like they're generated by a product of local unitaries, which is a different sense of local. Do we know anything about those kind of unitaries, which are produced by products of say two local unitaries? by several layers, let's say. So there is some limit there on, um,
I
but
think,
it's a different sense of locality.
yeah, I think I see what you're saying. As far as I know, there is not, like, our work does not immediately imply something for that yet. Kind of, you're saying my unknown unitary U need not be like a low degree just in terms of the poly basis, but I do know for a fact that U is produced by several compositions of low degree small unitaries.
Yeah, yeah. I mean, the
Oh,
most trivial case is that I just do an X gate on every single qubit. Now that has a poly term that's, total weight, but it's trivially a product. Um,
yeah,
and then, of course, a product of C naught gates, or two layers of C naught alternating gates, kind of gives you these products. Maybe something interesting to look at if we don't know the answer.
yeah. I don't think we know the answer to that question. Yeah, as far as I know, we haven't looked at that.
Okay, great. Yeah, folks, feel free to post your questions in the chat, especially if I missed them from earlier. We can bring them back up. These, some of these speedups are very interesting. Well, actually, before that question, the sense in which this is quantum machine learning is maybe a different sense, or help us draw the connection from the way that we typically think of machine learning, and kind of this learning of the states, learning of quantum data, so to speak, as opposed to like doing some classification, or SVD, or maybe other forms that one might think of.
Yeah, that's a good question. Like, kind of like I'm kind of me. I wouldn't say I'm overselling, but neither would I say I'm underselling. The point is, I think, for example, like, let me just say one result that I had here, like on learning low degree unitaries. This entire slide was very motivated by just classical computational learning theory of Boolean functions. So even classically, people have looked at learning Boolean functions, low degree Boolean functions, and the protocol that they have is almost very similar to what's happening quantumly. We just kind of observe that you need to do something structurally more for quantum setting that they didn't need to for classical Boolean functions. So in a way, I would think most of the questions that we have been looking at for quantum states is very motivated by people by classical learning themselves, but they weren't motivated by that in the first place because they weren't dealing with these kind of problems that we do. So they didn't look at it. So kind of, I would say, like, it's extending classical learning theory to the quantum framework when you have non-commutative objects.
Awesome. And maybe a final question here about noise. So in the presence of noise in the unitaries and the circuits, I suppose your sampling complexity goes up, which starts to eat away quickly at your speed up or advantage. How much do we know about the effect of noise on all of this?
So that's a good question. Like, that's one of the also the reasons why we introduced the statistical query model. Like, for example, so if you just look at this model, like I just said, like, okay, tau, you can think of tau as your noise parameter in some sense. So like you get this pristine expectation value out, but the point is you can have some noise in it. So the question is, in the statistical query model, so inherently the statistical query model kind of handles noise as well in either preparation of the quantum system or in measurement noise. For example, if I have psi tilde of C and I can only perform M tilde, maybe that is close to my unknown expectation value up to some metric tau. And the question is kind of like the statistical query model kind of handles, like, if I have all these noise into it, can I still learn certain quantum objects? And you can. The point is, although I say stabilizer states, I gave a negative results, there are several other class of quantum states for which we do have positive results as well, that means we can handle noise in those systems as well, like learning procedures.
Okay, yeah, thank you. Yeah, so I guess you'd have to use some kind of mitigation, which increases your sample complexity
Exactly.
at the level, because otherwise your noise isn't bounded in the median. It's your tau is just going to go to expand until you reach, because everything usually damps with under incoherent noise towards zero, or
Exactly.
um, um, oh, quick final question from Shashi. Hello, Shashi. This learning states requires quantum computers to prepare and measure them in a specific way, like Bell sampling. What about learning that doesn't depend on Bell sampling? I think that's the question. Feel free to elaborate.
I mean, there are several other learning procedures. For example, the original tomography procedure, that is not based on Bell sampling. That is based on using some Kyle tomography and things like that. So there are several learning procedures. The ones based on stabilizer, even for stabilizer states, there are certain procedures that don't rely on Bell sampling, but Bell sampling is one way where I kind of highlighted it because like kind of there are several subsequent works like from this year and last year that use Bell sampling to just go beyond learning stabilizer states. But that is not like the only procedure that people have used for learning.
Excellent, Srinivasan. Thank you so much and congratulations on, again, the wonderful work.
Thanks.
Folks, you've been great in the chat today. I didn't hear any jokes, so drop your favorite quantum joke. I haven't gotten a laugh out yet. But thanks for all the discussion and questions and lively interactions. As always, this will stay recorded, so you can go back and rewatch it. But the only time you can be live is Friday at noon Eastern time. So click like and subscribe to know what's coming up. And with that, have a wonderful day.
Thank you.